pleasure to have Nicola in the Institute. It's the first time in Mexico, in fact. So welcome.
Thank you.
He's going to talk us about the geometric loci and moduli spaces of curves.
Thanks a lot for the introduction, and thanks a lot for having me here. It's a big pleasure to be at UNAM and in Mexico City. So I'm going to talk about the geometry and combinatorics of moduli spaces of curves. So I will start by giving an introduction to the topic. So the first part will be a very brief and short introduction about the history, the motivation of the problems. So I will talk about what I will mean by curves and their moduli spaces. And in particular, I want to explain all the words in the title, that is the geometry of the moduli space and the combinatorics of the moduli space. And then later I will give like a selection of my results on subvarieties of moduli spaces of curves, and namely cohomology classes. Or moduli spaces of curves. So let me first start by what do I mean by a curve. So let's start by clarifying the language. Does this work? Good. So by a curve, I will mean a Riemann surface a Riemann surface C is a compact connected complex manifold of complex dimension 1. Okay. So viewed as a complex manifold as a dimension 1, that's why we call it curves. When you look at it as from a real manifold, it will have it as real dimension 2, so hence the name of a surface. So graphically, how an object of this type looks like this. So it has attached to it, it comes with a number, the genus. So the genus G is defined as the number of holes of C, of the Riemann surface C, viewed as a topological surface. Okay. So in this case, we have G is equal to 2. So this is one way of giving curves, thinking about curves. Another way is we can think about curves as C can be viewed as the solution set of a polynomial equation So what do I mean by that? You have an equation of this type with x and y are complex variables. And you think about C, or curve C, as being the solution set of this equation, plus, so the solution is you take the solution set plus a finite number of points at infinity. You want to compactify. So our surface is a compact manifold. So if you just take the solution, then you need to add also the point at infinity, and there will be a finite number of them, plus few points at infinity. So let's look at an example of how to produce a surface of this type. For instance, if you start with considering an equation of this type, y squared equal to product I from 1 to 6 of x minus ai. Okay, so here what I'm saying is I'm picking a sub I complex numbers. For every, there are 6 monomials of this type. For every choice of 6 complex numbers, I have an equation of this type. And hence I look at the solution set of this equation, I compactify it, and I obtain exactly a curve of genus 2, like in the picture over here. Okay. So this example is important because it brings to our attention that the point of the philosophy of the game, which is curves don't come by themselves, but rather they come in family. Why is that? Because here, if I pick for every choice of the A sub I, for every 6 tuple of complex number, I produce a curve. But if I vary the 6 tuple of complex numbers, I can vary my curve. So all curves don't come by themselves, but they rather come in family. So the picture to have in mind is something like this. Think about here the base of the family to be 6 copies of C. And for every 6 tuples of complex numbers, A1, A6, I look at an equation of this type, and I produce a surface in this way. Okay. So this is to say that what is important is to look not at just specific curves, but rather all curves at once, all families of curves at once. And so the object here of study it was natural then to consider the moduli space of curves. MGN, this is the notation, the standard notation. This is the moduli space of smooth curves of genus G. So the first index here is the genus of the curve. In that example, the genus was 2. And together with n marked points. So this is the object to study. The points of the moduli space consist of isomorphism classes of a Riemann surface together with a choice of n marked points. So I'm looking at object of this type plus P1, P2, P3, n points of the curve. Okay, so now I have defined this as a moduli space. That is, points in this space are to be thought as curves together with marked points. Now, what is important is that this object was first introduced by Riemann from 1857. And Riemann knew that this is not just a set. It's not just the set of isomorphism classes of curves with this marked point, but it has a richer structure. And so essentially, let me write down a first approximation of the correct answer. Essentially, MGN is a complex manifold of dimension 3G minus 3 plus n. This is already Riemann 1857. So let me be careful here. I'm saying essentially because this is just a first approximation of the answer. The correct answer is MGN is an orbifold, so it's a quotient of a complex manifold by the linear action of a finite group. So we need to be a little bit careful. But we are not too far off as a first approximation to think about it as a complex manifold. So locally, there are charts. And what is important is that this is not just in a set of points, but it makes sense to talk about nearby points. You can move from an object of your space to a close by, to a nearby point. So as in this picture over here, as you vary your 6 tuple of complex numbers, you produce another nearby curve, which topologically looks the same. It's still genus 2, but the complex structure is different. So what is happening in the moduli space, you are fixing the topology of the object and change the complex structures. So if you are interested in studying objects of this type, then you are naturally also led to consider singular curves, curves with singularities. Why is that? Well, let's just make an analogy. Let's complete the examples here. What happens when some of the AIs coincide? Just by looking at the equation, you see that your solution set is singular. We produce a singular surface. So let's look at here, for instance, the 6 tuple of numbers given by 0, 0, 1, 2, 3, 4. As the first two AIs coincide, the solution set of the equation is a singular surface. a singular surface that can be represented, for instance, like this. So this is a surface that has been obtained by possible topological way of obtaining it is the following. You take a loop here, you contract this loop to a point, and you obtain this singular point over here. Okay? So why is this point singular? So locally, locally, the curve there can be looked as the solution set of the equation xy equal to 0 in C2. So when I will mean nodal point, I will mean points which in the local neighborhood they look exactly this way. Okay. So after Mumford, now I will skip many chapters of the history, and go directly to 1969, when the linear Mumford considered like a space or moduli space of bigger objects. So as you can see here, the problem is that the issue here is that the space is not compact. So we can look at families of curves, but the limit, not all limits are smooth. Some limits are singular, which means your space is not compact and you want to look for a compactification. How do you compactify the space? You need to throw in you want to look at not just smooth curves, but you need to throw in also singular curves. But do you want all type of singular curves or just a subset of them? So this was the problem that was solved by the linear Mumford, and namely they constructed this space mg and bar. Well, the notation suggests that this is the compactification of mgn. So this is the moduli space of stable. So the magic word here is stable, and I will define this. Stable pointed curves. So the statement is that this space is compact and contains mgn as an open dense set. That is, you are adding exactly the limit points, nothing more. Okay. So what is stable? What is a stable curve? Let's make the definition. So we want to look at still pointed curves. Now the curves don't have to be necessarily smooth. So C. So let me write it in this way. Okay. C P1 Pn. This is an element of mgn bar. What it means to be stable. Stable means the following. There are some conditions that have to be satisfied. C, so points of C are either smooth or nodal. By nodal point, I mean exactly a point like we have seen over here, right? So locally is the origin of the solution set of this equation, which means locally your surface looks like transversal intersection, transversal union of two copies of C meeting at that point. Or it can be smooth, of course. So this includes the smooth curves. Okay, then I'm requiring. So here there is. Remember that there is always like a Riemann surface together with a collection of mark points. I want all the mark points to be smooth. I don't want the mark points to be singular. This is a condition that you impose. So each pi is smooth. And the third condition is that there is a finite automorphism group. Your curve has a finite automorphism group. Your pointed curve has a finite automorphism group. That is, you look at the automorphism of the curves, preserving the points, and you want a finite number of those. So this condition actually is very simple to rephrase in combinatorial terms. Yes?
What does it mean P is smooth?
Once again, either smooth.
PI is smooth.
Oh, PI is smooth. So remember, PI, the points here that I'm considering together with the curve, I want them to be smooth points. So what does this mean? So the way to think about C is the following. C is you can think about it as being many components, many smooth curves meeting at nodal points. This is a singular point. This is a singular point. Every other point is smooth. So my PI should avoid those nodal points. Mm-hmm. So for instance, this one here, it could be P1. Mm-hmm. I want to say a few words about this finite automorphism group. This is a combinatorial condition that is easy to check. Namely, every rational component should have at least 3 special points. That is, either nodal points or marked points. Like in this example, this is a rational component. This is supposed to be a sphere, a Riemann sphere. And as you can see, there are 3 special points, 2 nodal points and 1 marked point. So there is a finite automorphism group here. Once you fix 3 points on a genus 0 component, there is no automorphism. On any genus 0 component, you want that condition. And on any genus 1 component, you want at least 1 special point, where again, special point means nodal or marked. Marked is one of the PIs. Every other component of your curve is fine. Was there a question? Any comments on here? So this is an example of a stable curve. And so this is an example. Let's say there is a P1 here. I can put here a P2, a P3. So this is an element of, let's count the genus of this curve. So this is a component of genus 2. This is genus 0. And this is genus 1. And there is no loop. So this is a genus, there is a total genus 3. And there are 3 marked points. So this is an element of M3 3 bar. This is all I want to say about the geometry. Very short for long history. And now I would like to say something about the combinatorics of this space. As you can see here, I start already counting the genus was simple because we just summed up all the genera of the components. But in general, you need to do something else. So let's go in that direction. So let's talk about the combinatorics. MGN bar is stratified by topological type. What do I mean stratified by topological type? Stratified means that I can think about it as being the union of strata, where each stratum consists of curves with the same topological type, the same topological structure. Let's make an example. So I can look at all curves which topologically look like this. And I can look at the stratum of all the curves which look like this. Okay? So what do I mean by that? This is the locus of all curves which look like a genus 1 component meeting in 2 points, a genus 0 component coming with 2 marked points. Okay? So this is an object, this is a stable object. Every genus 0 component has at least 3 special points. The genus 0 component there has 4 special points. We are fine. This is stable. The genus 1 component has 2 special points, 2 nodes, so we are fine. Altogether, this is an example of a stable curve. Right? And now the important object, I can look at topologically, all curves which topologically look like this, but they have different complex structures. So I look at the stratum inside, the total genus here is 2, and there are 2 marked points. I look at the stratum of all curves of genus 2 with 2 marked points, which look like that. And I can parameterize this stratum by a graph, namely the dual graph of this configuration. How do I get the dual graph? I put a vertex for corresponding to every component. There are two components, two vertices. Every vertex comes with a label, namely the genus of the corresponding component. There is a genus 1 component and a genus 0 component. And now for every node, I'm going to put an edge connecting the corresponding vertices. I see two nodes here, which meet, where the two components meet. It means that I want to see here two edges linking the corresponding components. And finally, so this is the data, this parameterize all. I want to represent by this graph the stratum. There is also the mark points. The mark points will be represented by legs. And each leg will come with a label as well. So this is leg 1 and leg 2, corresponding to P1 and P2. So the idea is that moduli space of curves are stratified, and each stratum is represented by a graph. So this is when the combinatorics starts to kick in. Okay, so now what are the major questions? So the first big question was asked by Mumford in the 80s in his last paper in algebraic geometry. And what he proposed was study the cohomology ring of the moduli space of curves. Here I'm taking the cohomology with Q coefficients. Okay, so what is this object? This is an algebraic object. The cohomology is just an algebraic tool which helps us to study the topology of the space. Can we say anything about the cohomology of this moduli space? And it turns out that this is too hard. So already in his first paper, he realized this is too hard, so forget about this. Why is this hard? It's already hard to find a set of generators for the cohomology group. There is no, at the moment, we don't know a list of generators for this group. So he suggested a simpler problem. He suggested to reduce the problem to something else, and namely, he suggested to look at a subring. So this is a subring of which he called the tautological ring. Okay, what is the advantage here? The advantage is that this subring is given as the subring generated by an explicit list of generators. We know the generators, we are fine here. So we solve that issue. And at the same time, so this is defined as a ring generated by some elements, some cohomology classes. At the same time, we didn't reduce too much. He didn't reduce too much because he showed that many interesting cohomology classes lie in this subring. So as a first approximation of the ambitious general goal, it makes sense to study this ring. And this is already interesting enough and mysterious enough. So let me show you how a generator like this works. So let's think about tautological classes. Examples. There are two types of examples that we have. One that we have already seen. You can look at the cohomology class of the boundary strata. And I will call these boundary classes. So the boundary strata are subvarieties. You look at the cohomology class of that subvarieties, that's already an element, a cohomological element, and that's in the subring of tautological classes. There is another geometric way of producing classes, which is look at Chern classes of vector bundles. Okay? And namely here there is a final list, final collection of Chern classes of vector bundles on MGN bar. It's very explicit, right? It's very geometric. So let me show you, I would like to do a picture to show you how you would like to take the ring generated by objects of this type, so generated by boundary classes and Chern classes. Now, the boundary strata, as we have seen, can be represented by graphs. So I will use the graph also to note the boundary classes, the classes of the boundary strata. So this is an example of a tautological class. And I also want to intersect this with Chern classes of vector bundles. And in order to represent this combinatorially, I'm going to decorate the graph. I'm going to insert some decorations on the graph. The decorations will correspond to Chern classes of vector bundles. And so let me give an example of generator of the tautological ring. So I'm going to look again, I'm going to look at a graph of, as we have seen before. This is a boundary stratum, so I take the class of the boundary stratum, and then I'm going to put decorations here. So these Greek letters psi and L, so the decorations comes in two types. There are the decorations which are attached to the vertices, and the decorations which are attached to an half edge or to a leg. They correspond to different type of Chern classes of vector bundles, and those are vector bundles that basically parameterize how the complex structure of a component varies, or how the position of the leg, of the node of the point corresponding to the leg varies. So very briefly, maybe let me zoom in this example just to give you a feeling of how what this decorated graph corresponds to. So I will look at a graph of this type. And what I can do is I can do the following operations. Basically, I can cut in half the two edges. And if I do that, I produce the following graphs. Okay, and here, say you have plus, plus, minus, minus. Upon gluing the plus together and the minus signs together, you obtain the original graph. Now, what shall I think about these two graphs? Well, I can think about this as representing the moduli space of genus 0 curves together with 4 mark points. That's a stratum, it's the full moduli space. And I can think about this as well as representing the moduli space of genus 1 curves together with 2 mark points. Now I have, if I have vector bundles on each of these two spaces. I take Chern classes of those vector bundles, and that will give me these classes here. Sorry, this is the lambda is attached to the vertex, the psi is attached to a leg. So those are Chern classes on these two spaces, and I pull back these two Chern classes via these two maps, and I obtain a cohomology class of this type, which I can think of as being an element in the tautological ring of M2 bar. Okay, so what I want to say with this picture is that there is a concrete list of generators for this tautological ring, and this generator look like decorated graphs. So this is the language that I want to use. And now, finally, let me arrive at the main philosophy. So the philosophy is the following. The philosophy is that classes, cohomology classes of geometric subvarieties govern the geometry of MGN bar. Okay, so what do I mean by that? So this is the philosophy that I follow. And the idea is that if you look, there is a specific collection of subvarieties that I'm going to call geometric subvarieties. Why geometric? Because they are cooked up in a geometric way. If you look at the classes of geometric subvariety, they govern the geometry of the ambient space MGN bar. So they give you a hint that it's a key to study the global geometry of MGN bar. So what do I mean by a geometric subvariety? So the moduli space of curves is the family of all curves of a fixed genus with a certain number of mark points. If you fix a specific geometric property, which is not verified by all curves, you look at all curves verifying a specific geometric property that gives you a subvariety of your moduli space. That's a geometric way of constructing a subvariety. Let me give an example. I'm going to discuss the example of Hurwitz loci. Hurwitz loci, Hurwitz subvarieties. What are those? So I'm going to look at H, K, G. This is a locus. It's a subvariety of MG. And it's defined in the following way. I want to look at the locus of all curves of genus G such that a certain geometric condition is satisfied. Namely, there exists a map from C to P1, the Riemann sphere, of I have used G as being the genus of my curves. I have to use the letter K. I want my map to be of degree K. Okay, I look at all curves of a fixed genus which admit a map of degree K to P1. Now, if the genus is positive, K can be 1. That's one of the first exercise, one of the first properties that we study in complex geometry. But K can be 1, but can be at least 2. Okay? And then you are asking yourself, what happens if I look at the locus of all curves satisfying these properties? Is this a subvariety? Do I get all the space, or is this a subvariety? So this property, this locus, was studied classically. And in fact, the first result about it is due to Beniamino Segre. So here we go back at the beginning of the Italian School of Algebraic Geometry in 1928. And what Beniamino Segre tells us is that the codimension of the Hurwitz locus, HKG, is G minus 2K plus 2. I'm assuming that K is at least 2, otherwise the locus is empty. Okay, so let's look at this condition over here. What does this mean? This means that if you choose K small enough with respect to the genus, the codimension is positive. So you get a proper subvariety of the moduli space of curves. Okay. So here I'm assuming that if you get a negative number, it means that you don't have a proper subvariety, but rather you have all the Hurwitz locus is all MG. So we are interested in the case, of course, we are looking at subvariety, so we are listing in the case when here you get a positive number. So let's look at which numbers you can get. So let's look at when the codimension is 1. And this case was studied by Harris Mumford. (1982). That's one of the major steps in the study of the birational geometry of MG bar. Let me tell you what they do. Well, they compute an explicit formula for classes of Hurwitz loci when the codimension is 1. So you look at the formula over here, you solve for K in the case when exactly you get codimension 1, and they get you an explicit form. What this means, an explicit formula? We talked about the fact those classes turn out to be tautological. So their formula, their classes can be written as a linear combination of decorated graphs, exactly the language that we have seen here, right? So their classes will look like a linear combination of decorated graphs where coefficients are polynomials in the degree K. And they give an explicit formula for this, and this was used in a certain way to deduce results about the global geometry of MG bar. Now, my first contribution in this field was to look at the next non-trivial case. So for many years, people didn't do anything in this direction. And the reason was the following. First of all, there is a certain complexity of the computations when you go high in codimension. The complexity increases just because you have a bigger number of generators. And also, it was not clear how to apply computation in higher codimension. So my first result was the following. My first contribution to this field was an explicit formula for Hurwitz loci when, in the next non-trivial case, when the codimension is 2. So the formula it's a closed formula where it's a linear combination. It's written as a linear combination of decorated graphs of codimension 2. The coefficients are quadratic polynomials in k, in the degree of the map here. And it's explicit. And but besides the computation, instead of showing you the formula, let me show you a concrete application of this formula. So the first consequence is the following. Corollary, the Hurwitz loci, Hurwitz classes of codimension 2 are not in the ring generated by codimension 1 classes. Okay, so what is this telling us? This is telling us that if you just look at codimension 1 classes, they are not telling you everything about the geometry of this space. There is more of the geometry of moduli space of curves, which is not detected by the study of only codimension 1 classes. So it makes sense to go up in the codimension. This was the first hint that something is there that has not been detected. And also, let me give an explicit geometric application. It's a consequence of this corollary that if you look at your Hurwitz classes or Hurwitz loci of codimension 2, you may ask, okay, you are a codimension 2, so maybe you are intersection of one divisor with a second divisor. Could that be possible? No, this corollary is telling you, no, that's not possible. You cannot realize your codimension 2 Hurwitz loci as intersection of two divisors. So one more time, the geometry of the geometry of MGN bar is not detected by only the divisor. You need to look at more type of subvarieties. You need to go higher in codimension. This was my first contribution. Now let me tell you a little bit about other ways of constructing subvarieties. This is a way using Hurwitz theory. You can do other type of things regarding looking at other geometric properties of curves. So I'm going to look at what I will call Weierstrass loci. And again, I need to start by a geometric property which is not satisfied by all curves. So in this example, I'm going to fix the genus to be 2. And as we have seen at the beginning of the lecture, curves of genus 2 can be seen as the solution set of an equation of this type. Plus few points at infinity. The point that I want to make is that every genus 2 curve comes with a distinguished set of 6 points. If you look at the points of coordinates a sub I, comma 0, there are 6 of them. Those are called Weierstrass points. So every genus 2 curve has a collection of 6 Weierstrass points, those Weierstrass points over there. Okay, so this is a geometric property. Using this geometric property, we can construct a subvariety of MGN bar. How? Similar to what we did in the Hurwitz case, right? So we look at all the curves. I can define the following. Wn. This is the locus of n pointing curves of genus 2 such that I'm requiring that all the mark points are Weierstrass. Each pi, all the points that I'm choosing are Weierstrass. Each pi is Weierstrass. So each of them is one of this type. So n can be at most 6, right? Because all the pi's are distinct. Okay, so what do we get? Do we get a subvariety here? Yes, because since there is only a finite number of them, which is Weierstrass, being Weierstrass is a codimension 1 condition. It's a codimension 1 condition that you impose at each mark point. You are imposing them at n mark points, which means that you have n divisorial conditions. It turns out that they are all disjoint, they are all distinct, independent. And so this locus here has codimension n inside M2n. You can look at the closure of this locus inside M2n bar. And again, this is a geometric way of constructing a subvariety. So let's see what we know about this. And the divisorial case, the case of codimension 1, as always, was already treated in the literature. And the first contribution here is due to Eisenbach and Harris. We are in the 80s, 1987. And again, what they have is a formula for explicit formula for the cohomology class of the case when n is equal to 1. You take the closure of this locus, the divisorial locus when n is equal to 1. Okay. Why is this important? This was for many reasons. So let me tell you this story here. Rulla, in his thesis from 2001, showed the following result. If you look at any codimension 1 subvariety, codimension 1, any class of a codimension 1 subvariety, lies in a cone. It's a polyhedral cone. So it's generated by 3 rays. If you look at classes of subvarieties, they form a cone, because sum of 2 classes of subvarieties will be still a class of a subvariety, the class of the union of the subvarieties. And if you take a positive multiple of subvariety, that you define that to be as well part of the cone. And so what happens is that if you look at any class of a codimension 1 subvariety, lies in a cone generated by 3 rays. The 3 rays are spanned by the class of W1 bar, the class of the Weierstrass points, and then the class of, there are 2 other rays which will correspond to boundary strata, namely the only 2 boundary strata that are there, the 2 graphs that you can write with only 1 edge. You can do this in 2 ways of genus 2 with 1 mark point. So you can do 1, 1, and here 1 leg. The other thing that you can do is 1 and do a self node and 1 leg. Those are the only 2 graphs that you can do with only 1 edge. So what is interesting is the point of this of this result by Rulla is that this is not just an arbitrary example. When n is equal to 1, this generates an extremal ray of this cone. So it's not just an independent example, but it helps you to find the structure of all classes of divisors of codimension 1 subvarieties in this space. So it makes sense. Certainly, why don't we start to go higher in codimension? And so I started here looking at the first non-trivial case, which is the case when n is equal to 2. And this was 2014. I produced an explicit formula for this class. Okay? So again, I will not write down the formula. It will take me about 5 minutes. Again, it's a linear combination of decorated graphs. Now the graphs come either with 2 edges, so they are codimension 2, or with 1 edge and 1 decoration. Decorations will be codimension 1, so this is the type of object that how they look like. But again, let me mention why this is important. Why the computation is important. Why from the computation we can obtain geometric consequences about the study of the whole moduli space. So just using the formula, from the explicit formula, and this was in collaboration with Dawei Chen from Boston College, we obtain the following result. For every n, so the formula here is only for n is equal to 2. But still, just using the case n is equal to 2, we deduce a result for every n. For every n, you look at the class of the Weierstrass loci for every n. This class spans an extreme array of cone of classes of subvarieties of codimension n. In M to n bar. So this is an exact generalization of the case n is equal to 1 that we have seen here. In every codimension, again, one more time, these classes, those examples of Weierstrass loci, they are not arbitrary. They are not arbitrary examples, but they are fundamental because they tell us something about all classes of codimension 1 or subvarieties of codimension 1. So we know nothing about cones of classes of higher codimension. This is one of the first results in this direction, where we can describe a little bit the structure of everything, of all the classes of subvarieties of that codimension. And as a result, as I said, this uses in an essential way this computation, just the computation in the case n is equal to 2. But also it tells us that those loci are interesting. They're not just arbitrary examples. So it would be interesting to find an explicit formula for those as well, right? Can we write down an explicit formula? Now, this is where things start to get hard, because if you look at the generators of the tautological ring, the generators of the space where you are, and as you increase the n, they grow exponentially. The number of generators grows exponentially. So you need to be careful. For this type of computations over here, I was doing sort of intersections of moduli spaces of curves. I was intersecting every codimension 2 subvariety with a dimension 2 subvariety. Every intersection gives us a linear constraints on the coefficients. Doing enough intersections, you are able to solve for the coefficients. But you can't do that every time for every n. As the number of generators grows exponentially, that's just not feasible. So you need to find out you need to find out some strategy. Okay? And this is the problem that I addressed and solved with at the next stage, at the next step. So let me tell you a little bit about that. So this is in collaboration with Renzo Cavalieri from Colorado State. And the formula is for every n, it's an explicit formula for all the Weierstrass loci. The idea is to use a recursive argument that allows us to get the general formula from the case n equal to 1. So just using the case n is equal to 1 and using a geometric recursion suggested from the geometry of the subvarieties, we obtain this numerical result of producing explicitly the class. So let me tell you, I'm very excited about this formula, so maybe let me spend 2 more minutes to say how it looks like. It's a closed formula. And just for the example, let me give you a way to appreciate the structure of the formula. Let me give you the formula instead of considering the moduli space of curves of genus 2 with n marked points. Let me look at a sub-moduli space, which I'm going to call M2n compact type. Namely, this is the locus, this is the moduli space of stable curves, but whose dual graph is a tree. So just for simplicity, we have the formula on our M2n bar, but just for simplicity, I will show you the formula on this smaller moduli space. This allows me just to get rid of all the graphs which are not trees, so all the graphs which have loops. Okay. And the formula looks like this. So for every n, the class of Wn bar in the tautological ring of this moduli space of curves of compact type is the degree n part of, I'm going to write down a formula in mixed degrees, and in order to get the class, you need to take the degree n part of it. So the formula is expressed as a sum over all gamma inside the set of trees which are dual to curves of genus 2 with n marked points, right? So every vertex comes with a label, and there are legs which will correspond to the marked points and comes with label. You sum over all these graphs. Remember that every graph corresponds to a boundary stratum. So this sum is topological in a certain sense. There is another sum, which is just a numerical condition. And I'm going to write down, so once you take every tree comes with a set of vertices, edges, and legs. For every leg, there is going to be n legs. For every leg, I'm going to attach a decoration at the leg, decoration I, which is going to be a formal series in a formal variable t. For every vertex of the vertex set of gamma, I'm going to attach a decoration at the vertex set, which will be a formal series in a formal parameter t. And for every leg, similarly, for every edge of the graph, similarly, I will have a decoration. So all the decorations are series in formal parameter t, and I'm going to take the coefficient of degree t to the power j. I'm summing over all the j's. Okay. So each series here, each decoration is a series on t. The coefficients are Chern classes of vector bundles on moduli space of curves. So when you look at the degree n part of this formula, this gives us exactly the formula that you want. So as you can see here, there is a rich combinatorial structure that you have to exploit. And also the formula suggests a rich combinatorial structure that you can generalize in general to consider a bigger class of subvarieties. So the advantage of the formula is that it's a closed formula. That's the same formula that holds for every n. And what is important is that you don't decide that the way you assign the decorations is the same, no matter which graph you pick. And the other important advantage is somehow I told you that these graphs are defined only for n up to 6 because there are only 6 Weierstrass points. Still, this formula makes sense also when n is bigger than 6. It gives the class of an empty locus, so it should be 0, which means that it gives you a relation in the tautological ring. Great, so now this brings me to somehow a look ahead. On what comes next. So this suggests that we have seen now many examples of subvarieties for which we have explicit expressions. Now, what would be interesting is to look at collections on subvarieties and identify combinatorial structures of collections of classes, combinatorial structures that allow you to compute the class, to get explicit formula, like in this example over here. So identify combinatorial structures on generating functions of cohomology classes. So one example, one of the big examples that is a source of great inspiration, of course, is the Witten conjecture, Kontsevich theorem, which is about generating function of top-dimensional intersections of moduli space of curves. And that result is so important because, for many reasons, but it's beautiful because it identifies the combinatorial of that generating functions as detailed from dynamical systems. Okay. So that's the case from top-dimensional intersection, but why don't we do that for every other choice of codimension? So what I'm proposing here is to look at generating functions of classes of arbitrary codimension and study their combinatorial properties. Another interesting direction is the following. So as I've discussed from the beginning when we define the tautological ring, there are two ways of producing classes geometrically: the boundary strata and the Chern classes of vector bundles. Similarly here, so far today we have discussed cohomology classes, which are classes of subvarieties of the moduli space of curves. But the other source of examples is Chern classes of vector bundles of moduli spaces of curves. So why don't we look at Chern class? Why don't we look at constructing vector bundles of moduli space of curves and study their geometric classes? So one of the famous examples is the class of, so here I should write down Chern classes, study of Chern classes of vector bundles. On moduli spaces of curves. And this is one of the topics that is very close traditionally to algebraic geometry in Mexico, namely the study of vector bundles on a fixed curve. What is interesting is that study how, by varying the curve, you can construct in this way vector bundles on the moduli space of curves and look at their properties. And one of the major examples here is given by conformal blocks, vector bundles of conformal blocks. What are those? Very briefly, those are geometric objects that you construct starting from representation theory. You start from the representation theory of finely algebras, certain type of non-commutative algebras. That's your input. And the output is a vector bundle moduli space of curves. Why is this important? If you look at their Chern classes, they satisfy remarkable combinatorial properties. They satisfy a certain number of certain properties that allow you to determine those classes, to reconstruct those classes from any G and every N, starting from lower genera, lower number of mark points, just from genus 0 and 3 number of mark points. So that's an example of a combinatorial structure that you can have in a set of classes. Now, what I would like to do, in the literature, people have studied conformal blocks of representation of finely algebras. What I'm currently interested in is to look at a little bit more general. You can attach in a similar way, you can construct vector bundles starting from representation of a bigger class of non-commutative algebras, for example, vertex operator algebras. That's another focus that is very well represented in mathematics in Mexico. I would like to tell you more if you are interested about my interest in this field. And namely, let me conclude by mentioning the final goal is to identify geometric information encoded in higher codimension. So I hope that I have convinced you in this talk that the geometry of a space is not just detailed by the codimension 1 subvarieties, but there is more to it that is not detected by the codimension 1 subvarieties, but goes higher in codimension. So at the moment, there is no theory for higher codimensional classes and how to interpret those results. The case of moduli spaces is particularly interesting because there you can produce geometrically or distant varieties, and you can have an intuition about what is going on about the general theory. Great. Thanks a lot for your attention.
When you are talking about your notes,
Yes.
Can you do an ugly point there, more singular?
Yes, yes. In fact, there are studies which include other type of singularities. So that condition that I put like just simple nodes, that was very simple type of nodes, and that's enough to cook up a compact moduli space of curves, right? So all these moduli spaces that I've talked today are about those type of curves with only nodes. So there the moduli space is already compact. But of course, you can throw in more type of singular curves. You can go higher. You can more complexity. And in fact, if you look at the idea, the general philosophy is that if you throw in more moduli spaces of curves, you get contractions of these spaces. So those curves with a higher number of singularities, with higher type of singularities, are obtained by starting from this and contracting some subvarieties. So it's certainly very, very interesting to look at those. At the moment, this is part of ongoing study.
Okay, thank you.
It's, again, very well represented here in Mexico by researchers in Oaxaca, for instance.
Any more questions? So you said the formula you obtained for the class of W2 was done by intersecting with Mumford classes.
Dimension 2 classes, correct. With dimension 2 classes and obtaining linear relations in the coefficients, yes.
But, so how do you know it's in the tautological range?
Oh, that's a great question. So, so all classes that I've discussed today are in the tautological ring, right? So of course, that should be like an input, right? If you start from an arbitrary class, how do you know whether it is there or not? So there are two ways. Either but if you have a way of producing the class without using that information, you can exhibit it in that way. That is, if you have like a sort of like, so for instance, the way how we cook up this formula, we don't use that class. You don't use that fact. And it comes out if you want from that fact. All what we use in this formula, is the only input is the case n equal to 1, which is tautological, because when n is equal to 1, when in codimension 1, everything is tautological. Since this formula recursively cooks up the general case from the codimension 1 case, automatically tells you that those, we already knew that before, but that's a way to, for instance, is a way to prove it. In general, there is like a big result by Faber and Pandaripande, which tells you that all loci of curves which are obtained by looking at maps to P1 with a certain type of ramification conditions at the mark points, all of those are tautological. So the Hurwitz loci, tautological. In the Weierstrass, you can as well look at them as the locus of genus 2 curves with a map to P1 ramified at the Weierstrass point. So again, they will be tautological. But in general, correct, in general, this is an interesting question. What happens if you come with a non-tautological class? That's extremely interesting. We don't have at the moment a way to deal with non-tautological classes. There is, at the moment, this is subject of ongoing research. How to deal with them, how to express their intersection theory, and their relationship with the ring of tautological classes.
Any other questions?
Yes, please.
This in relation with the graph, with the singularization of the curve. There is something.
Oh, I see what you're saying. Yes, absolutely. So what happens is that when you normalize your curve, basically you are cutting all the edges. You are cutting all the edges, and you are left just with vertices, with half edges and legs.
Is the same procedure?
Absolutely.
The singularization.
Absolutely, it's exactly the same. It encodes that topological procedure. So the graphs are just topological. They don't see anything about the complex structure.
More questions?
Please.
The codimension 2 classes, you mentioned that those are not, they're not products of the codimension 1. How do you prove
Great question, yes. Great. So, yes, in codimension 1, all the relations are known. Yes, great observation. So actually, but that corollary, it's a 1 second corollary, it's a 1 second proof, it's a 1 line proof. And it's an immediate consequence of the formula. Since the formula has the coefficient of a certain class is non-zero, then it cannot be in the ring generated by codimension 1 classes, because everything which has, there is a certain class which detects whether you are in that ring or not. And if your class has a non-zero coefficient in terms of that generator, then you're outside of that ring. So once I got, you need to know that, correct, absolutely. There I use the fact that I know all the relations, yes. So I should say that in general, the relations are not known. So this is one of the big open problems in the theory. There is a list of relations which is known, but it's not clear whether those relations are all or not. So that's, again, that's an important open question. But in codimension 1, we are safe. Codimension 1 and 2, we are safe.
Anyone else? So what other sorts of geometric conditions? So you have the
you can do all, correct. You can, there is a plethora of examples that you can come up with, right? You specify a map to P1 or to any curve, and you impose ramifications and mark points. That's Hurwitz-like, correct. That's one way to do it, correct. Oh, if you are looking besides Hurwitz, well, then you need to start from a geometric property of curves. You need to start from a property that not all curves are satisfy. So that is why it's so important to know the geometry of curves. You start from the classical geometry of curves, and in that way you can produce subvariety. So something else that I've looked up, for instance, in my other collaboration with Dawei Chen from Boston College, was a study of subcanonical points, which come up from study the canonical models of curves and the singularity of the canonical models. So that's different than Hurwitz. Theta characteristics, exactly. So what we look is curves which are like where points have a certain type of specific type of behavior with respect to some theta characteristic. And then you can distinguish between odd theta characteristic and even theta characteristic. You have different components of moduli. So that's all part of a theory which is related to dynamical systems. And right. So I have some results. I didn't mention that, but we have some results there as well, some computations. That's another source of examples.